So, hello everyone, welcome to CppCon. My name is Shen. I'm from Google LLVM team, so I'm doing the compiler work. But I'm also maintaining libstdc++ regex library as part of my open source contribution. So today, I'm going to talk about regular expression implementations. So before proceeding to the actual talk, let's look at the several annotations. So for tuples, we're going to use parentheses. For lists, we're going to use square brackets. For sets, we're going to use curly braces. And for maps, we're going to use arrows. All right. So a while ago, I saw this Stack Overflow outage that is caused by a regular expression. So the regular expression matches one or more characters or one or more characters. So it's a fine expression, regular expression, even if it's a bit redundant. But Stack Overflow used a backtracking regex engine, and which is problematic because it results in all of n square behavior. And all of n square behavior is sufficient to take down Stack Overflow for a while. All right. So we'll come back later to see why this happened. In this talk, I'm going to introduce the data structure we're going to use for compiled regex and the 4 different algorithms that run on this data structure. After that, we should be able to understand why Stack Overflow is taken down. And after that, I'm going to talk about 3 regular expression features that you should be aware of because they slow down your program, and how should you deal with them. Last but not least, I'm going to talk about 2 changes I wish to make into the standard so that we have faster and easier to use regular expression library. All right. So why don't we look at the compiled regex representation? We call this non-deterministic finite automaton. You can find the formal definition from any theory of computation books, so I'm not going to repeat that here. Instead, I'm going to show some code examples to help you understand that. So an FA is a directed graph, and the nodes or the states, by the way, I'm going to use state and the node interchangeably here because they are the same thing in the context. The state stores data, including the type of the state and optional data members for each individual type. And of course, successors. So the state types are like accept type, match type, accept state, match state, alt state, alternative state, and repeat state. Each of these type represents a regular expression feature, and there are a lot more than these ones, but we're focusing on accept state and match state. So why don't we look at the example of the simple regular expression AB. So the graph is dumped by libstdc++ regular expression debug info. So it's the real data generated by the library. So you may safely ignore sbegin and send here. Those are just different nodes for implementing capturing groups. And here our focus is state 1 and state 2. Those are blue because those are matching states and they match A and B respectively. So state 5 is the accept state, which indicates a successful match. So the second example I'm going to give here is A or B. So the alternate operator creates a diamond structure that starts from 6 and forks into state 1 and state 3, and finally converge to whatever comes after that, which happens to be state 7, which is S-end, but it can be anything that's after the sub-expression. The third example is repeat A. It creates a loop structure that starts from 2, and for 0 or more times, it enters 1 and comes back to 2. Then it exits to state 4. Similarly, state 4 is just whatever comes after the sub-expression. All right. So this is an interesting example. We have a question mark repeated for 3 times and a repeated for 3 times. Notice that a question mark means the optional a, so we either match an a or we skip it. So it creates a triangle structure, and we concatenate these 3 triangle structures and 3 matching states together. This is interesting because from 0 to state 11, which is the accept state, in total we have 8 different paths. That means we have 2 to the power of 3 different paths, because at state 1, 3, 5, we have to make individual decisions, and those decisions combine to 8 different scenarios, which is exponential. And we'll come back to this later to see how does it slow down our algorithms. And the final example I'm going to give is a compound example that shows how different structures can compose. So on the top level, we do a repeat structure, and the subgraph for the repeat graph is an alternate operator, which forks into state 2, which is matching A, and state 4, which matches B. Those 2 states come back to 8. When 8 exits, it exits to state 9, which matches C. All right? So let's talk about regular expression matching algorithm. A regular expression matching algorithm takes a regex and a target string. In our example, the target string is ABAC. So the algorithm is supposed to find a path from 0 to 12, which is the accept state, such that all the matching states in the path matches all the target characters in the target string. For example, if we have such a path from 0 to 12, we have matching states 2, 4, 2, 9. They are in order, and they are matching A, B, A, C. And that's what we are going to match for the target string. All right, and how do we find such a path then? And the first algorithm I can come up with to find a path is depth first search. It's the textbook algorithm. It traverses the graph in a depth first order. So why don't we just go through an example? So it's the same example. We start from 0, and we can proceed to 8 without consuming any characters. Our current target character is A because we start from the beginning of the target string. And we proceed to 7. Notice that at 8, we have a choice between proceeding to 7 and 9, and we go to 7 first because we are using this greedy strategy for the repeat state. Greedy strategy is defined by many of the popular flavors of the regular expression, for example, JavaScript style or Perl style. So we go to 7 first. Then we have another choice between 2 and 4, and we go to 2 first because we go to the left-hand side of the alternate operator first, defined by some of the flavors. So we go to 2. Now we are going to find a match here because we expect an A, and we do have an A character in the target string. So we find a match, and we proceed to repeat state. So we go to 7 again, and we go to 2. Unfortunately, it is a match for this time, so we backtrack. And then we proceed to 4, which is a match again. So we go back to 8 again. We go to 7. We go to 2. Yes, this time it's a match. So we go back to 8 again. We go to 7. And we go to 2. It doesn't match. So we backtrack. And we go to 4. And it still doesn't match. So we keep backtracking until we exit the repeat state. And we find state 9 matches the final C. Now we proceed to 11 and finally 12. That's how we find a path that consists of all the target characters. So that's a match, a successful match. And why don't we just look at the code? It's not hard. So first we check if our current state is accept state. If so, we just return true because that's more or less by definition. Then we check if the current state is match state. If it is match state, but the target character doesn't match our expectation, then we should early return false without proceeding to the next state. If it is a match state and the characters match, we should increase the target iterator, the target pointer here. So either it's a match state and we with our target pointer increased, or it is not matched and we shouldn't increase our target iterator. We can proceed to the next step, which is recursing on the successors. If any of those recursive DFS calls returns true, we can safely return true. Otherwise, we return false. All right, so it's like a 5-line DFS. So let's look back to this pathological example. As I said before, the number of paths is 2 to the power of 3, which is 8. So imagine that instead of repeating the separate parts for only 3 times, we repeat them for n times. And what will happen? Now we have a number of paths equals to 2 to the power of n, which is pretty bad because DFS algorithm will have a very bad time, especially when n is large, like 32. It takes like 1.5 minutes to run with n equals to 32. So the time complexity is exponential, and if you're running your application with the security concern, then you're screwed. So how do we solve this problem then? So a very usual idea is that if you have an exponential algorithm and you want to make it polynomial, either memoization or dynamic programming. So if you have a function like this, which is pure, thank God it's pure, and we can make a container for memoization out of the signature, where the container itself is a map, and the key is the inputs of the function, and the value is a return value of the function. All right. So this is a conceptual map from a pair to a bool, but in C++ we can implement that in various ways. For example, we can go for the straightforward way. We use map and pair and bool. Or if we are aware about the performance, we can use a 2-dimensional array where the first dimension is the ID of the state. So ID starts from 0. And the second dimension is the position of the string character. So because we have an immutable string, we can easily use either pointer or an index to represent the whole string content or the suffix of the string. Or we may have other different data representations depending on our optimization scenario. So for illustration, I will just use the worst choice. I will use this STD map from a pair to bool here. So we are going to write our memoized version of DFS. So first we create the key. Then we check if the key is already in the memoization container. If that's the case, we don't proceed to the actual computation and we just return the value. Otherwise, we compute the value and store the value back to the container. DFS info is exactly the same as our previous DFS version, except that it doesn't recursively call itself. It recursively calls our memoized DFS, so that during each recursion, the memoization logic is picked up. All right. It turns out the time complexity, as we expect, is much better. It's the number of target characters times the number of states. By the way, the number of states is proportional to the length of the regular expression strings, with one feature disabled. We will talk about that feature later. But the space complexity is also increased because we have to keep this 2-dimensional memoization container in our memory. And that could be bad because what if we have a very long target string? Say, if the target string has 1 million characters, then we are going to have a bad time and run out of memory. And we are able to solve this problem. So look at this 2-dimensional memoization container for DFS. So during the DFS, we go back and forth in this two-dimensional table. When I'm saying back and forth, I mean we may go down or go back up. So we don't always go horizontally. And that's a problem because by using this access pattern, we have to keep the whole two-dimensional table in the memory. And what if we change the order of the traversal? Instead of keeping all the things in the memory and going back and forth, we keep only one row in the memory. In this case, we keep the second row in the memory, and we are during the process to generate the third row. And after completing generating the third row, we can safely discard the second row. And in this case, the first row is already discarded. That means we cannot feel free to increase our target iterator because that's gonna move our row down, and that's bad. So our strategy is to exhaustively search for the current cells in the current row and collect all those potential cells that's able to proceed to the next row. Then we proceed all at once. All right. So based on this idea, we have to create a helper function that's called epsilon closure. An epsilon closure is a function that takes a set of states and returns another set of states. The returned states are reachable from any input states by at least one epsilon moves. A epsilon move is any move that doesn't consume any target character, or it doesn't increase the target string iterator. All right, so I don't have code for this in the slides because I think that's straightforward enough to implement. So let's look back to this pathological example. And we can just run through the BFS algorithm to see how it goes. All right, so first we initialize our container, which is a set. It contains one start state. And we call our epsilon closure. So it computes all the states that are reachable by at least one epsilon move, which means 1 through 7. 8 is not in this result because from say 7 to 8, we have to consume a target character. So after that, now that we have exhaustively searched the current row, we find those states that are able to proceed to the next row, which are the matching states and matching A, because A is our first target character, all right? So we filter all the epsilon closure states by matching states and by A. We find the result to be 2, 4, 6, 7. Then we assign back the result to the active set and do the similar things for the second character. So we calculate the epsilon closure. In this case, from 2, we can reach 3 through 7. From 4, we can reach 5 through 7. From 6, we can reach 7. From 7, we can reach 8. And we finally merge all these results together into 3, 4, 5, 6, 7, 8. Then we do our filtering, and the result is 4, 6, 7, 8. All right, and we do the similar things for the third character. We calculate the epsilon closure, and we filter them by the third character. And we have such states. All right. So now that we have run out of target characters, we can do another epsilon closure because epsilon closure itself doesn't consume any target characters. As you may see, 11 is in our final epsilon closure. That's a good thing because we actually find a match because 11 is there. It's more or less by definition. So if we do equivalently, if we do a final filter by accept state, we can get a non-empty set back. That means we have found a match. And here's the code. It's actually even shorter than the DFS version with the help of the epsilon closure helper. So first we initialize our container. Then for each character, we call epsilon closure, and then filter the result by the target character. And finally, we do our final epsilon closure and check if accept state is in the epsilon closure. All right? So the time complexity actually doesn't change because conceptually we still need to traverse to fill in each cells in this two-dimensional memorization table. It's just that we don't have to keep the whole table in the memory. We just need to keep one row. So the space complexity reduces to all of the number of states. All right. One caveat is that though the worst case time complexity is the same as the DFS and memorization version, it's actually slower than the DFS on average. By saying on average, I mean on the normal, non-malicious, non-pathological inputs. In those cases, DFS usually have just a few backtracks or even no backtracks at all, and it quickly finds the answer and early returned. But on our DFS algorithm, we have to exhaustively search the current row and then proceed to the next row. So it's actually hitting the worst case much more frequently. And how do we solve that problem? We do have a way to speed up our BFS approach, but with the price of space complexity. That's called deterministic finite automaton approach or DFA approach. So the idea is quite simple. We simply pre-compute this expression in our BFS code so that we make it faster. So the pre-computation generates such a container that's from a pair of a set of states and a character, and it produces another set of states. So there's another trick we can do here to normalize different sets of states to unique IDs, where ID starts from 0 and ends at n-1, where n is the total number of sets of states we care about. And this is easy to implement in C++. We just use a vector of a fixed length array. The column number is 128 here because we are dealing with ASCII characters here. And dealing with Unicode is a slightly different question. All right, so let's see how can we generate this DFA. Be aware that this is the pre-computation, so no target string is involved. First, we calculate the ID of the given set. So it may be a new ID allocated or the existing ID if it's already seen. So if the ID is in the DFA, we shouldn't do that again, so we just early return. Otherwise, we create a new DFA entry and we start to populate the entry. So we enumerate all the characters in the ASCII and we calculate the expression to get the result set back. Then we calculate the ID of the result set and assign the ID back to the corresponding cell. All right? Finally, we recursively call on the result set. This is because we want to lazily discover new sets so that we don't have to exhaustively search for all the sets, enumerate all the sets in our space because there are too many. With that said, even if we do this lazy discovery, the worst case space complexity is still bad. It's 2 to the power of number of states, which is exponential. And unfortunately, we do have at least one malicious input to hit this worst case. So if you have a regular expression to match arbitrary content followed by an A or arbitrary literal followed by a fixed length suffix, then you're hitting this worst case space complexity. But the upside is that we have a much better matching time complexity. It's just all of them because if we go back to the BFS approach, if the function body only takes O1 to run, then the whole program takes ON to run, where n is the length of the target string. All right. So here's the matrix of all the algorithms and the performance characteristics. So I have 3 suggestions for this. First, don't use DFS or DFA without a backup solution because they have exponential behaviors and they will cause the security vulnerabilities of your application. Secondly, if you do want to choose a backup solution, you want to look at the length of the target string first. For example, if you are doing a code search, line-wise code search in your code base, and you have a style guide that says each line should be less than or equal to 80 characters, then the number of target characters is less than or equal to 80 characters. So in that case, it's pretty safe to use DFS and memoization. But if it's not the case and you have a potentially long target string, you should use BFS as a backup solution. And now let's see why the Stack Overflow outage happened. So it uses our DFS algorithm without memoization, and it results into, in theory, exponential behavior. It's only all of n squared because it repeats the part for only 2 times. If it repeats for k times, then we have our algorithm run on all of n to the power of k, which is exponential. And here's the implementation and the algorithm matrix. So as you may notice, most of the implementations implement DFS because many features they claim to support or they wish to support is only implementable in DFS mode, or at least efficiently implementable. And some of the implementations, for example, libstdc++ and PCRE, they do support BFS, but with BFS mode turned on by, say, custom flags, the corresponding features will be turned off. So if we use both BFS feature and those, BFS mode and those features, I guess the compilation will fail. So for RE2, which focuses on security, it takes a very different approach. First, it tries to compile the regex to DFA. If that fails because it generates too many DFA states, then it falls back to DFS and memoization with a memory consumption threshold. I think the memory consumption threshold is 32 kilobytes, and it's not customizable. I wish it's customizable. So for example, if I have 8 megabytes and it's dedicated for one important regex, so why can't we just use that? Because DFS is faster than BFS on average, right? If DFS and memoization threshold is hit, it falls back to BFS. All right. So let's talk about customizations, or the features that slow down your application. The first one is capturing groups. It's actually very common, so it serves as these parentheses that keeps content of the last match so that you can inspect the content after the regular expression matching. So usually we have a global match, which is put into the group 0, and we have individual contents put into individual cells based on the capturing group parentheses. So before supporting this feature, for each algorithms, we have such a nice container, which are affordable at least, and we have to modify them to support this new feature, like this. So for DFS memoization, that's actually pretty cheap. It's almost free to support because we can just maintain one list of strings as capturing groups during the whole regular expression matching. That is because we are doing this in a DFS way, right? We can modify the container to represent the next capturing group we want to use before entering the recursion. And after leaving the recursion, we can revert all the modifications very cheaply. But for BFS, we don't have such a luck because we don't have a current state thing. And we actually have different states with their own capturing groups. Those are totally different. That means for each state that's currently on record, I have to add a overhead for that. And the overhead has a factor of number of capturing groups. So if you have 1 million capturing groups, you're pretty much screwed. But for DFS, we don't have this problem. For DFA, on the other hand, I don't have a solution that doesn't maximize the time and space complexity. So the best solution I can have will decay the time complexity to the BFS one. So why don't we just use BFS? So I do have some premature ideas, but I don't want to talk about that right now. So how do we prevent the customizations? We should check, if we are using BFS, first of all, we should check the number of capturing groups to make sure they are a small number by looking at, for example, std mark count. And for DFS, we don't have to worry about that. The second feature I'm going to talk about is backreferences. So, sorry, I have a mistake here. So the backreference refers to a specific capturing group by the number in it. For example, we have \1, so it refers to it matches the content in the first capturing group at that time. So for AAB, the whole regular expression matches it, and the first capturing group matches the first AAB, and the back reference matches the second AAB. It does not match AAB, AB, AB, because the first part and the second part don't equal. All right. So let's do this again. Before the modification, we have these nice containers. Now, after the modification, we have to put path into the consideration because the contents of them start to matter now. But that actually defeats the purpose of our memoization, because the whole purpose of memoization is to reduce an exponential case to a polynomial case. But with those paths considered, the memoization itself is exponential. So why do we even do this? So the solution is to, if you really care about the security, is to forbid it, because it's actually proved it's only supportable in an exponential way. It's NP complete. So libstdc++ provides this library extension flag that is __ polynomial, which switches to the BFS approach and throw an exception if it sees a back reference. So the third feature I'm going to talk is brace quantifiers. It uses braces in enclosing a number, and it acts actually like a macro that expands the expression that it associates with for so many times. For example, A3 expands to AAA, and the interesting part is when we nest those quantifiers. So it expands to 9 times if we have such a thing. And sometimes you have like parsers to check for this pattern and you want to avoid this pattern, but users can always work around that by putting parentheses and extra characters. So it's not actually avoidable. And what if the user do this? And this will be bad because with such short regular expression input string, it generates so many states. And because all of our algorithms rely on the number of states. So if the number of states is huge, then we're going to have a bad time. Well, the solution is easier. We can simply forbid it through the library flags, or the library should set up a state limit. For example, some of the standard library sets up the state limit. So if the actual states exceeds the limit, the compilation will fail and throw an exception. Here it is error space. All right. So as a conclusion, I have a matrix here. For DFS, it can support everything. It's free because it's already slow. For DFS and memoization, it can freely support capturing groups, but for other features and other algorithms, those features are either limited support or not supported at all. But for DFA memoization, for DFA and capturing groups, I need to put more thoughts on it. Or if anyone knows the answer, tell me. I'll be grateful. So let's talk about the future. I really want to changes on the the standard, so that we can have better things. For example, in the future, I want static compile time regex. So I want this compile time regex that carries no runtime data and carries all its characters in a template, so that the library authors can actually do code generation, and the compiler will pick up all the code patterns in the regex code and optimize all of them. And the use case should be like, we can just construct a static regex and pass it into the normal regular expression function call. And that actually requires a language change, because currently we do not support arrays as template parameters. And it also comes with a library change, but that's trivial. It's trivial to you, but not trivial to us. And today we can do similar things, but not as nicely. We can use variadic templates, and we have to separately write each individual characters. But with that, I actually have a 81-line proof of concept. It doesn't do parsing, so that's why it's so short. And it runs much faster with those unoptimized library implementation. And I believe Boost.Xpressive is doing some manual optimization that can pick up this very simple case, which is just matching 1000 A's with the A star. And why that's so fast? Because the compiler can seize the code pattern in the regular expression library and do all kinds of optimizations: loop unrolling, loop vectorization, constant propagation, inlining, and many other cool things. So if we don't have compile time regex, another approach to take is to write a JIT compiler. Write a regex engine that uses a JIT compiler to compile to machine code at runtime. But to standardize JIT compiler, it's a bit hard, or even harder, much harder than my previous proposal. So that's just to give you a feel how this proof of concept look like. It's not based on MFA, it's using CPS style, continuation passing style. That's why it's so short, but I'm not going to talk about the details here. All right. So the second feature I want is to extend the algorithms for non-characters. For example, I have such an event, enum, that models a machine repair case. So we can open a case and close a case, and during the case, we can swap parts and reboot the machine. I want to be able to match such an event stream. That is, during a case, we rebooted the machine for 3 times in a row at some point, so that I don't have to reinvent the algorithms in my project, because those algorithms are written and optimized. I want to be able to just use them. And that is the second feature. Currently, basic regex requires the element type to be car-like. It's much stronger than a equitable type. So yeah, here's a brief recap. We have our 4 algorithms with the performance characteristics and the suggestions of when to use what. And then I've talked about 3 different features. How should we deal with those features so that they don't slow down our application? Finally, I have 2 wishes of the changes to the standard, so that we have faster and easier to use regular expression library. And that's all about it. We have like 20 minutes for questions. Yeah.
On your static regex, the change to the standard you proposed was char arrays as template parameters. Something else that you could use that may be coming real soon, because Louis Dion is championing it, is a new kind of user-defined literal.
I know what that's happening. So the comment is that instead of supporting the car arrays in the static regex, we can use a lightweight version, which is easier to support. That is, making this user-defined literal support variadic cars, I guess.
Yep.
Okay, support variadic cars. So that we can just write a string literal with a suffix _re or something, and it will generate the static regex object for you, so that we don't have to separately write each individual characters.
I actually have a question on what you do in the static regex. Does it produce a different type depending on the input?
The question is, in the static regex implementation, do I use different types for different input? The answer is yes. I use similar things like expression template. So for each individual compile time input, I will generate a unique type for that. So if you are interested, since we have time, we can go through or just look at the implementation, because we do have time.
Is it like on GitHub or something?
Yes, it's a guest, actually. Well, let's just wait and yeah. Well, we can still do questions while waiting for that.
You can disconnect your Wi-Fi and reconnect. That's probably what you do.
Oh, that must solve everything. I mean, restart. I hope that it's helpful that Google Slides support offline mode. But other questions?
How do you feel about the non-ECMAScript parameters, and would you support a proposal to deprecate and remove them as fast as possible?
The question is, do I support to remove the non-ECMAScript styles? That means POSIX styles.
Yeah, grep, bgrep, basic, extended, and all.
Oh,
Yeah. How much do you hate them?
slightly, mainly because the leftmost longest matching style, and that's harder to implement than the JavaScript style. And I do support to deprecate them and just don't use them. And I'm not happy with Pro style either, because it supports like look ahead, which is actually backtracking look ahead, as opposed to a static look ahead, which returns a true or false for once. And nope, no, it's just a completely out of a network. But anyways, you can look at the code after the talk. It's I will send out the slides, so you will be able to get the link. So any other questions here?
I got a orthogonal question, since you started this talk with like a security mindset or something like that. I am a PCR user. I've used it in several projects. It's used everywhere. PHP uses it, Apache uses it, etc. What scares me, it's a great library, it works, but what scares me is that it's maintained by 1.5 people per time.
Okay.
Yeah, something like that. Yeah. So I'm basically suffering like from the OpenSSL problem that nobody's actually investing time into reading the code, checking that there are no weird overflows in there, and being sure all the libraries that you showed before are all currently properly maintained, or yes, I know that the one some of them are, but the overall status looks like a bit strange in terms of actual code reviews on them and being sure that actually the code is sound, rather than throwing random regular expressions on them and then checking out, yeah, okay, you got a pathological case that makes it crash.
So what is your question?
Amongst the libraries that you showed at the beginning of the various implementations of that, would you recommend, would you say that all of them are getting the necessary attention not to have weird overflows or underflows when you're doing this kind of backtracking?
I mean, I can't speak for others because I'm maintaining. Sorry, the question is, it's more or less scary to use those the libraries that are not actively maintained, or if bugs are in those libraries, then if they are not fixed on time, then it's pretty scary. So that's your comment, right?
More or less, but it's just my observation. My question was about, well, amongst all the libraries that you listed at the beginning, and all of them are using a depth first search.
Yes.
That makes me nervous, basically.
But
there's almost no safety net in there.
So that's also a comment. So the comment is, for almost all these libraries I list, they use depth first search for as the default regular expression engine. So yes, so that's the comment.
So, let's catch up later. I will elaborate on that.
Okay. Yes, and for my first suggestion on this matrix is to not use DFS or DFA without a backup. And how many engines without a backup show up here? Like 4, right? So question?
If you want Wi-Fi, I have tethering on my phone because of Java bar, and then you can show them with GIF.
Okay.
Maybe you have to join other members.
Oh, wait, sorry. Here. Hey, it works. So I don't want to teach all of details about this code because it involves template programming and like template specializations and continuation passing style. I actually stealed it from a SML book. It's just the first example that SML book gives. So it creates different templates for different nodes we are going to use. Someone also call it parser combinator, but I'm not sure of that. And we just specialize on different cases and handle different cases using CPS. We don't have to use CPS if we have coroutines. And as I said, I didn't do the parsing. So in order to use the regular expression, I have to explicitly write out the AST of the regular expression. All right. Any other questions? Yeah.
It'd be really great to have compile time parsing so you could generate errors in compile time.
The comment is it would be great to have compile time parsing so that we can actually generate error messages at compile time. And I think we do have that. That's called const expr. And we can put like static asserts in it. Yes, okay. Here.
This is a question that I asked you via email a while back. You didn't cover it, so you probably don't have a great answer. But given that each of these libraries uses a specific algorithm that has some killer regex, if we're accepting regexes from the end user, we have to, in some way, sanitize them or put resource limits on them to prevent our program from blowing up. Which of these libraries offer like ways to control these resource limits, or what is the best practice for how to avoid blowing up your code just because you got a regex from the user?
So the question is, if we are accepting the regex and the target string from the end user, or potentially the malicious user from the internet, which library should we use so that it takes care of all the resource management and other security vulnerability concerns? Is that the question?
Either it takes care of it, or it has like a list of things for us to check first. You know, if it says you must check that it has no more than 10 backslashes, I can check for that. But if it just says, I might blow up, that's not a good answer.
Yes, so the comment is either it can takes care of the resource management, or it exposes different like configurations for the user to set threshold on. So the answer, I guess, is RE2. So it doesn't expose much configuration for you to set threshold on, but overall it doesn't explode. So for the malicious inputs, that's what I'm saying. question?
Can you tell us a little bit about what is RE2? I haven't heard of it before. I'm familiar with PCRE. Does RE2 provide something that resembles the standard interface?
RE2, the question is, can I explain more about RE2? RE2 is not a standard conforming implementation. It's a third-party regular expression library developed in Google. It focuses on, it doesn't, for example, it doesn't support back references at all because it has security concerned. So it focuses on security and it uses DFA by default.
Is it available outside of Google?
The question is by saying it, you mean RE2?
RE2.
The question is RE2 available outside of Google? The answer is yes, it's open sourced with BSD license. Okay.
So RE2 is different than RE2C, which is like pre-compiled regular expressions?
So the question is RE2 different from RE2C? I don't know RE2C.
It is different. Okay.
So someone answered, yes, it is different. No questions? 1, 2, 3. Okay, you are dismissed.